Hello, everyone. I'm Jack Heslin, founder of the online community, The AI Conversation, and welcome to day 3 of our series, AI 101. Today, we're scaling the next block of our AI pyramid, neural networks and deep learning. Remember the machine learning basics we covered last time? Well, now we're taking it up a notch with technology that's actually inspired by how our brains work. Neural networks are a pretty big leap forward in computing. They go beyond the traditional algorithms to systems that can spot complex patterns on their own. Over the next few minutes, we'll check out how these technologies, tick, why they're such game changers, and the cool ways they're being used right now that you might not even be aware of. You might recall when we were doing machine learning in our second module, we compared machine learning to a strong, reliable Clydesdale horse. Well, neural networks are more like an octopus. Give me a second to explain. With all those flexible arms working together like interconnected neural pathways, it's a perfect metaphor. Octopuses have their own neurons spread throughout their entire body and arms, not just in their head, kind of like how neural networks distribute processing across layers of artificial neurons. These amazing creatures, the octopuses, adapt to all sorts of environments, just like neural networks can learn from all kinds of different data. When octopuses solve problems, they try multiple approaches at once. That's exactly how neural networks tackle complex problems, from different angles simultaneously. Now, before we go too much further, we really should define our relationships. Let's clear up something that gets people a little confused. What's the difference between neural networks and deep learning? Why are they in the same block? Neural networks are comprised of systems inspired by our brains, built from artificial neurons that talk to each other through signals. Deep learning is specifically about neural networks within layers, what we call deep neural networks, which can recognize more complex patterns than simpler networks. Think of it this way. All deep learning systems are neural networks, but not all neural networks are deep. It's kind of like all jets are planes, but not all planes are jets. They share the same foundation, but they differ in complexity and what they can do. That's really important. That's why we've grouped them together, though, in our AI pyramid. Now, as we go forward, we should keep in mind that the underlying concepts of deep learning and neural networks are designed, this design comes straight from how our brains process information. In our biological neurons, we have dendrites that receive signals. The cell body processes them, and axons transmit those signals to other neurons. Artificial neurons copy this setup with inputs, processing functions, and outputs. Now, artificial networks are super simplified compared to the 86 billion neurons we have in our brains, times 8 billion people in the world. But they capture something essential. Learning happens when connections get stronger through use. This similar structure is why neural networks excel at things our brains do easily, but traditional computers struggle with, like recognizing faces or understanding context language. What makes neural networks so powerful isn't any single artificial neuron, but how they work together in the complex patterns they can spot through all their connections. As we go forward, we might want to realize that neural networks and deep learning make up the differences right now. Look at transportation. Those self-driving cars use neural networks to make sense of sensor data, spot objects, predict movements, and make driving decisions in real time. So this application isn't coming, it's here. Or what about voice assistants we all use, like Siri and Alexa and Google Assistant, excuse me. They rely on specialized neural networks to understand what we're saying, convert sound waves into meaningful text, and then come up with appropriate responses. What about healthcare? Well, that's where it's a game changer. These technologies are revolutionizing diagnosis through medical image analysis. They can detect diseases in x-rays and scan sometimes better than human doctors. All these examples show how neural networks build on basic machine learning, the first block in our pyramid, but enable completely new possibilities that traditional approaches simply couldn't handle. Now, there are many advantages to this. They're a big deal. Well, to begin with, they're amazing at modeling complex, non-linear relationships that would stump traditional algorithms, finding patterns in data that might be invisible to other approaches. They're also incredibly adaptable, like the octopus. You can apply them to tons of different problems, from identifying what's in a photo to predicting stock prices. Although we're not saying use deep learning or neural networks for your financial planning. We're not saying that. Deep learning takes things further by automatically pulling out relevant features from raw data without human help. No more tedious manual feature engineering that traditional machine learning needs. Again, we're building on the block. Perhaps most exciting of all, deep learning systems just keep getting better as they get more data and computing power. That's why we've seen such dramatic improvements in AI capabilities recently. This ability to scale up is a key reason why neural networks and deep learning are driving most of today's AI breakthroughs. But like any technology, there are always limitations, there are always challenges, and of course, we should address that. Now, in neural networks and deep learning, they face serious challenges, like what we call the explainability problem. They often work as what's known as black boxes, where we see inputs and outputs, but can't easily understand how or why these decisions are being made. The systems need massive amounts of training data to perform well, making them tough to use in areas where data is limited or, quite often the case, expensive to collect. Training and running a sophisticated neural network takes a lot of specialized hardware and a lot of power consumption. This raises the cost and raises climate change concerns. This isn't necessarily a green technology. Neural networks can also be fooled by what are called adversarial attacks, specially crafted inputs that trick the model into making confident but wrong decisions. And of course, as with all AI and all technologies, there's a big ethical concern. These systems can perpetuate or amplify biases present in their training data, raising serious questions about the fairness and privacy in applications that affect people's lives. But having said all that, this is a crucial second block, second layer in our AI pyramid. Neural networks and deep learning enable the more specialized technologies in the layers above. We can't get to expert systems without using machine learning, neural networks, and then we can get to expert systems to do rule-based reasoning, while natural language processing depends heavily on deep learning to understand human speech and text. Computer vision, which we'll explore in a few modules, runs almost entirely on something called convolutional neural networks that can identify objects and interpret visual scenes. But again, it builds on each previous layer. And that's a good way to look at AI. Each layer is a layer of AI, but each one as we go up the pyramid needs the one below it. In the next module, we'll check out expert systems, and we see how they combine the pattern recognition strengths of neural networks with the explicit knowledge representation. So, where does all this bring us? Where do we end up getting to? Kind of blocking out the slide there. Sorry about that. Neural networks are evolving in some super exciting ways. Excuse me. There's what we call neuromorphic computing, specialized hardware designed to mimic the brain even more. This will dramatically improve efficiency. And then what we call multimodal models that can handle different types of data simultaneously, blurring the lines between AI capabilities, creating systems that understand the relationships between text, images, and sound. We're also seeing smaller, more efficient models that could run sophisticated AI on devices with limited resources. Bringing these capabilities to smartphones, Internet of Things devices, and other everyday tech. Self-supervised learning approaches are reducing our dependence on labeled data, as we talked about in machine learning, while combinations of neural network through what we call symbolic AI are improving reasoning capabilities and addressing that black box problem through what we call increased interpretability, all of which we'll be talking about more in future modules. So, where are we now? These advancements are going to lead to breakthroughs in more general AI systems that can transfer learning across domains in ways similar to human intelligence. Now, nothing's going to match our 86 billion neurons, but for all that's already happened with this really extraordinary technology, in many ways, we're just getting started. Hope you enjoyed all that. Thank you for joining us. My name is Jack Heslin, founder of the AI Conversation. Come check us out at www.theaiconversation.com. Thank you.